This lecture is going to be about Eisenstein series and formulas with Eisenstein series, identities, stuff that we need to actually work with them. So the reference for everything I say is going to be this paper of Matthew Young from 2019 called Explicit Calculations. With Eisenstein series. And this does everything in great generality. We're going to make some assumptions. We're going to assume that we have weight 0, Eisenstein series, so that's k equals 0 in this. And I'm also going to assume that the level n is prime, which is a relatively restrictive assumption, but otherwise the formulas get quite messy, and I think it's better to just look at this case. And if you want the full formulas that just basically have a bunch of GCDs and LCMs in them, you can find them all here. So last time we defined this Eisenstein series, E ZS chi was the sum gamma in gamma naught n mod, the stabilizer of infinity, gamma infinity, of chi gamma, and then the imaginary part of gamma z to the s. And this is really just one of the Eisenstein series that we need to work with. There's actually an Eisenstein series attached to each cusp. And here so this is math frac A in LaTeX. It's a sort of a Gothic A, and it's usually what's used to denote cusps. And here what we have is another series definition, but we're going to have some symbols that we need to define. Instead of gamma infinity, we're going to have a gamma sub frac A, and then we've got our character, and then here we're also going to have this imaginary part, but then now of this sigma frac A inverse gamma z to the s. So what are these two symbols that I've defined here, or that I've written here? So for every cusp we have a stabilizer. So remember that the cusps are given by, well, you can take a couple of different representatives, but the cusps that we wrote down were u over w and what was it? What did I pick? One way, I'm not sure if this is exact. I think this is what I wrote down last time, but one set of cusps you can take is positive integers like this that are coprime, and you say that the cusp u over w is equivalent to the cusp u prime over w prime if and only if w is equal to w prime and u is equal to u prime mod the GCD of w and n over w. So here are some set of cusps. If n is prime, there are two cusps. And this gives you the cusps 1 over n and 1 over 1, but those are equivalent to I infinity and 0, which are the more convenient ways to write these two cusps. And for each cusp, you have a stabilizer. So gamma sub frac A is the stabilizer of the cusp frac A. So we saw that, well, we defined last time that gamma infinity was the group generated by 1101, maybe with a plus minus here. And well, let me just maybe this, okay. So we said gamma infinity was this, and of course this stabilizes the cusp at infinity. And you know, you can see this is the group 1m01 for integer. And for n prime, for level prime, there is it's sort of unfortunate here. I mean the stabilizer of the cusp 0. Right? It's not gamma naught as in gamma naught n. Just, you know, this is the whole thing. And here, what you can do is you can take this to be the group. So you can check that this stabilizes the cusp at 0. And these also have the property that sigma sub frac A, which is this what's called a scaling matrix. I haven't defined it yet. Gamma infinity scaling matrix inverse is equal to the stabilizer of the cusp frac A. And the other, so this is one property that we're going to require of our scaling matrix sigma frac A. And the other property that we're going to require is that when you apply it to infinity, this is the cusp I infinity, you get the cusp A. And so if you have these two properties, and additionally that your scaling matrix is an element in SL2R. So we defined SL2Z, not SL2R. SL2R is the set of 2x2 matrices with real entries, and the determinant has to be 1. So this this matrix in SL2R is said to be a scaling matrix. For the cusp frac A, if and only if, you know, these hold. So that's that's the definition of these things, and it's quite opaque. If you want to know exactly what, you know, explicitly what matrices you can choose, you can check Young, let me see which one it is. It's okay. Proposition 5.2. For explicit choices of your scaling matrices. And for prime n, you can take sigma infinity to be just the identity matrix, and then sigma 0, so this is going to be the scaling matrix at 0, at the cusp 0, take it to be 1 over square root n times 0 minus 1 and 0. Okay. Another reference for this is Iwaniec spectral methods. And it's, I think, section 2.4. And this also gives you a formula for these things. Okay, so we have these definitions of our gamma A's, which are stabilizers of the cusps, and these scaling matrices. So our Eisenstein series, you really have an Eisenstein series for a cusp, and it looks like this. And it's, you know, I sort of have to define these things, but we're not really going to end up using this very much. You know, maybe for a few properties here and there, but really these end up not being super useful. What's much more useful is knowing the Fourier expansions of these things. So the Fourier expansions are going to look like this was discussed in the lecture on eigenfunctions of the Laplacian. They're going to look like something times y to the s plus something else times y to the 1 minus s plus, and then you have a sum n non-equals 0 of something times square root y k Bessel function s minus 1 half 2 pi n y e to the 2 pi I n x. And so if, you know, this k Bessel function was defined also in the lecture on eigenfunctions of the Laplacian. And the question is, what are these quantities? Right? It's because there's sort of the structure theorem that tells us that we're guaranteed to get something that looks like this, and we just need to fill in these gaps. And this Fourier expansion, so this is a Fourier expansion. And this Fourier expansion is a lot easier to write down if you write it down the way that Young does it. And this is less common. Usually, pretty much always when people talk about Eisenstein series, they talk about Eisenstein series attached to cusps like this. But Young does all of his calculations with Eisenstein series attached to characters. So what he does is he defines for two Dirichlet characters, chi1 and chi2, E chi1 chi2 zs, and we're not going to use this definition at all, but sort of have to write it down. This is going to be a sum of over coprime integers c and d of, so here chi1 is a character mod, q1 chi2 is a character mod, q2, and the Eisenstein series attached to characters is defined to be this thing. Okay, and we are never going to use this, but it's good to know that this exists. The reason to consider these things is because the Fourier expansions for them are easier to write down. So, so this is an automorphic function on gamma naught q1, q2 with character chi1, chi2 bar. And then we're going to define this completed version of this Eisenstein series. So here I'm just going to write chi1, chi2, and I'm going to put an asterisk up here. And this is defined to be q2 to the s over tau of chi2 pi to the s. This is the Gauss sum. Times gamma of s L2s chi1, chi2. This is the Dirichlet-L function. And then times the Eisenstein series itself. And as usual, when we're talking about completed anything, completed L function, for example, the reason to do this is because these have nice properties, right? That the functional equation is nicer, for example. So these satisfy the functional equation that E chi1 chi2 completed zs is equal to E chi2 chi1. So you swap the order of the characters and you put a bar over both. And then you have your s goes to 1 minus s. And these things are meromorphic for all complex numbers s, and it's holomorphic if either of your characters is non-trivial. So essentially this is saying, this extends to an entire function. And so this is the functional equation. So this is sort of the usual business that you do with these things. You say, okay, we've got this series definition, and it extends to an entire function and has a functional equation. So this is what it is. And then the important part, which is the Fourier expansions. So these are, since they're automorphic functions, it turns out you can relate them to the usual Eisenstein series. And then, so I'm going to write 1 to be the trivial character mod 1. And so I'll say that Eisenstein series show character mod 1 and then some character psi it's convenient to put a bar here. Completed. It's at s, so here's the Fourier expansion. It is n to the s over tau of psi bar times, here this is the completed Dirichlet L function, 2s psi bar times y to the s, and plus n not equal 0, you have 2 absolute value n to the 1/2 minus s, and then here you have a sum of divisors function. And then you have the Whittaker function at the end. And then you're going to need the Fourier expansion of another one. You're going to need the Fourier expansion of this Eisenstein series. I'll define the pieces of this in a moment. So this Fourier expansion is going to be into the 1 minus s tau psi bar and d minus 2s psi bar y to the 1 minus s Of course, all of this you can get in Young's paper. This is just me going and tracking it down and transcribing it, basically. So this is all also for prime level. And you have the same Whittaker function. Okay, and the pieces in this, here I'm defining sigma sub s of n chi. This is the sum of divisors function. This is sum d divides n, and it's always going to be over the positive divisors. Maybe I should write d divides absolute value of n, just to allow for negative n, because of course here you do get negative n's, but just I'm gonna take the absolute value, and then this is chi d to the s. I'm also going to define sigma sum s of 0 chi to be 0, just for ease. Because often you're going to have these series, and I don't know, sometimes it's a little bit more convenient to not have to worry about omitting 0. And the other thing I needed to define was this completed L function. So this is going to be lambda of lambda s chi is pi to the minus s over 2 n to the s over 2, where n here is the conductor. So here I'm also going to assume chi is even and primitive. And so here n will be the conductor, and the completed L function is as such, and the reason to do it this way is because it ends up being equal to Gauss sum divided by square root n of lambda of 1 minus s Okay, so that should define everything in here. Again, for this K-Bessel function, this was discussed in the lecture on eigenfunctions of the Laplacian. And so, okay, we've got these nifty, nice-looking Fourier expansions for these Eisenstein series, the completed Eisenstein series attached to characters. But in practice, we really care about these Eisenstein series attached to cusps. So what we need to do is we need to translate from one to the other. And the translation for prime level is as follows. Have the I infinity ZS chi. So this was previous, or let me write psi. This was previously just called E ZS psi, but now I'm specifying this is at the cusp infinity. And again, here we're assuming that psi is going to be even primitive mod n. It's going to be n to the minus s E1 psi bar ZS. This is just what the theorem in Young's paper says. And then if you unwrap this, this is equal to tau psi bar over completed L function 2s psi bar of this is a trivial character in psi bar ZS. Okay. And this thing, this piece right here, this is what we wrote out the Fourier expansion here. So you can just multiply it by this Gauss sum divided by this completed L function. You get your Fourier expansion of your Eisenstein series at the cusp infinity. And then for prime level, there's only one other cusp. It's at 0. And Young says this is this Eisenstein series. And if you unwrap what this is 1 over completed L function 2s psi okay. And this also we wrote down what the Fourier expansion was right here. So this gives you the Fourier expansions that you're going to need for these individual Eisenstein series, and these are sort of the main computational tools that we'll need to get stuff done. There's one more thing that's gonna come up, which is that we're going to need the action of the scaling matrix sigma 0, which is essentially the Fricka involution. So Young says that if you have E chi1, chi2, and you act by the Fricka involution, then what this does is it just swaps the two characters around. Again, this is all assuming prime level, etc. And what this implies, using our relations up here, is that E I infinity sigma naught ZS psi is equal to the Eisenstein series at the cusp 0, but now you have it psi bar. Okay, so this was sort of a litany of just random facts about Eisenstein series, but these facts, especially the Fourier expansions, are going to be the main computational tools that we use. I mean, really, these two are the most important facts from this lecture. The other stuff is there mostly because it needs to be mentioned at some point. I need to define the things that that we're working with, but going forward, practically speaking, these two formulas are really just the main thing you need to worry about.